Hello everyone, this is Dr. G. Pranita, Assistant Professor of Chemistry, working in Government Degree College for Women, Begumpet, Hyderabad. Now I am going to explain about Sidjwick's theory and EAN and its calculations. Last class we were discussed about the Werner's theory. Werner's theory, it was explained about how the metal complexes will form, coordination complexes will form, and what are the properties of the coordination complexes, and what is the structure of the coordination complexes. This theory was explained very nicely. But this theory was explained based on experimental evidence rather than theoretical. So, even though this theory successfully explains the bonding features in coordination compounds, but it has some drawbacks. Coming to drawbacks of this theory, it does not explain why only certain elements form coordination compounds. And it does not explain why the bonds in coordination compounds have directional properties. And it does not explain the color of the complex and magnetic properties of the complex, and also not explain the stability of the complexes. These are the few drawbacks of the Werner's theory. So to overcome those drawbacks of the Werner's theory, next Sidjwick was given new concept. The theory is called as Sidjwick's concept of coordination. He has given in 1927 this theory based on bonding in complex compounds with the help of electronic theory of the valency. According to this theory, because the metal ions are not having inert gas configuration, so they are involving in complex formation. And also the bond present between metal ion and ligand is coordinate covalent bond. According to the Sidjwick theory, the bond present between metal ion and ligand is coordinate covalent bond. Here coordinate covalent bond is nothing but donation of electron pair from the ligand to metal. One is donor, another one is acceptor. That bond is called it as a coordinate covalent bond. Whereas here the ligand donates electrons pair to the metal ion, where M is represented as metal, L is nothing but which is called it as a ligand, and thus forms a number of coordinate bonds. And this Sidjwick's theory also explains the new concept that is called it as a effective atomic number. Then according to this theory, metal, almost all the D block elements which forms the coordination complexes, here all the D block elements have the vacant d orbitals, hence metals are acting as acceptors because of having the vacant orbitals. Whereas ligands are nothing but at least minimum to donate the one lone pair of electrons are called it as a ligands. Here ligands are calling as donor, whereas metal is calling as a acceptor. Ligand donates its pair of electrons to the metal and forms the coordinate covalent bond between metal and ligand. Here ligand like this, it forms the metal complex. If you see here in this complex, here platinum is a metal, whereas all the ligands which are donating one pair of electrons to the metals, because all are monodentate ligands, so they could able to donate only one pair of electrons and makes this bond. This bond is called it as a coordinate covalent bond. The representation of this bond is nothing but which is coordinate covalent bond is present between ligand and metal. Next, coming to effective atomic number. Effective atomic number is nothing but Sidjwick, he suggested that when ligands donate a certain pair of electrons to metal ion, the total number of electrons on the central metal atom, including those gained from ligands in the bonding, is called it as a effective atomic number of the central metal ion. Because while formation of the complex, ligands donates the electrons to the metal. So EAN is nothing but whatever the electrons present on the metal and whatever the electrons gained from the ligand, total electrons are calling as a EAN of the central metal ion. This rule can also be stated under two statements. One is, if the total number of electrons, that is EAN of the central metal atom, is equal to the atomic number of the inert gas, then such compound are stable and diamagnetic. Here inert gas is nothing but, in a periodic table, zero group elements like helium, neon, argon, krypton, xenon, radon are called as a inorganic gas. If EAN of any metal is equals to atomic number of inert gas elements like xenon 54, krypton 36, argon 18, then such metal complexes are stable and also which is diamagnetic complex. Suppose if the total number of electrons EAN of the central metal atom is not equals to the atomic number of the inert gas, then such compounds are unstable as well as they are paramagnetic. Coming to the calculation of the EAN of the central metal atom is equals to Z minus X plus NY. Here Z is nothing but atomic number of the central metal atom, where X is nothing but oxidation number of the central metal atom, where N is nothing but number of ligands, where Y is nothing but number of electrons donated by each ligand. This is the formula which is used to calculate the EAN. With help of EAN, we can come to know whether that complex is stable or unstable, whether that complex is diamagnetic or paramagnetic, we can say according to the Sidjwick theory. For example, if you see here this complex hexaamine cobond, in this complex, this is the metal, this is the ligand, this is the coordination number. In this complex, metal atomic number, that is 27, and in this complex ammonia is a neutral ligand. Whatever the charge is present on the sphere, the charge is equals to that metal oxidation number. So this complex oxidation number is +3. So according to the EAN formula, atomic number minus oxidation number, that is 3, plus N is nothing but number of ligands, that those are 6, into Y is nothing but each ligand donated, number of electrons donated to the metal. Here this is ammonia is a monodentate ligand. It would be able to donate only 2 electrons. So here we are writing 6 into 2. Here it is metal atomic number, oxidation number, here it is oxidation number, and here it is coordination number, here it is each ligand donated electrons. Metal atomic number, oxidation number, number of ligands, and each ligand donated electrons. So from this we will get 36. The 36 number is equals to atomic number of inert gas, that is krypton. Hence this complex is highly stable and also it is a diamagnetic. For example, if you see another complex here, in this complex hexacyanoiron, in this complex iron atomic number is 26, whereas here we have to calculate the oxidation number. Here cyanide is negative ligand, monodentate negative ligand, hence total 6 ligands are present, so -6, X minus 6 is equals to -4. Therefore, this complex oxidation number is +2. Whenever we are calculating the EAN, the formula is atomic number, that is 26 iron, minus oxidation number is 2, plus number of ligands, those are 6, and each ligand donated electrons are 2. Hence, by calculating this, we will get 36. So this, according to Sidjwick theory, this complex EAN also, EAN of the central metal ion also is equals to 36, hence which is also equal to the atomic number of inert gas. Hence this complex also stable according to the Sidjwick theory, and also which is a diamagnetic. If we observe these two complexes here, instead of writing on the sphere charge, we can write here like this also. Here it is a cation. If you remove the cation, we can write the charge on the sphere also. Both the complexes are same. If you observe the above complexes here, nickel tetracarbonyl, where iron pentacarbonyl, chromium hexacarbonyl. In this nickel tetracarbonyl, iron pentacarbonyl, chromium hexacarbonyl, now three complexes, there is no charge on the sphere. And carbonyl is a neutral ligand, hence no charge on the sphere, and it is a neutral ligand, hence no oxidation number. That is, oxidation number of these complexes, three complexes, are 0. And to calculate the EAN, the formula is atomic number. For example, if you calculate the EAN of this complex, here nickel tetracarbonyl, atomic number 28. Here 4 ligands are present, so 4 into each ligand donates 2 electrons. So 28, 4 2 8, 28 plus 8, 36. So this complex EAN value is 36. Whereas in this complex, iron is the metal, hence 26 is the atomic number. So no oxidation number, plus 5 into each ligand donates 2 electrons, 5 into 2, 26 plus 10, 36. Whereas in this complex, chromium 24 atomic number and no oxidation number, 6 into 2, 12, 12 plus 24, 36. So in these three complexes, here nickel 28 atomic number, so only 4 ligands are present. Whereas here iron 26 atomic number, so coordination number is 5. Whereas here chromium 24 atomic number, 6 coordination number is present in this complex. All three complexes EAN value is 36. That means which are equal to the atomic number of inert gas, that is the krypton. Hence all these three complexes are stable as well as diamagnetic according to the Sidjwick theory. Whereas if you see this example here in this complex, manganese pentacarbonyl, here in this complex, manganese atomic number is 25, whereas 5 carbonyls are present. So 5 into 2, 10, 25 plus 10, 35. So this is the unstable. 35 is not equals to the atomic number of inert gas, hence it is the unstable. So it tries to get the stability by forming the binuclear complex. It is called as a binuclear complex because here 2 metals are present. Such type of complexes are called as a binuclear complexes. So to calculate, for this also we can calculate the EAN. So here for such type of the complexes, we can calculate the EAN like this. Here 2 metals are present. So 2 into each metal atomic number manganese 25, that is equals to 50. Whereas 10 total ligands are 10. Here CO carbonyl, each ligand donates 2 electrons. So 2 into 10, 20. Whereas here in this structure, manganese, there is a sigma bond. Sigma bond is nothing but distribution of 2 electrons. So there is one sigma bond is present between manganese. Hence here only one bond is present. So 1 into 2 electrons, 2. Therefore total 72 electrons. When we divide by 2, so we will get the 36 for each metal of the EAN. Each metal of the EAN, that is equals to 36. So which is also equals to the inert gas atomic number, that is krypton, hence which is also stable. If you see this example, this is the bridged complex. In this example, if you see here radium metal, here which is associated with the 4 carbonyls, here this is called it as a sigma bond, whereas this one is called it as a coordinate covalent bond. Here sigma bond is nothing but distribution of 1 electron by metal and distribution of 1 electron by the ligand. Whereas this bond is formed due to distribution of 2 electrons by the ligand. Here it is a donor, here it is the acceptor. So we can also calculate such type of the complexes EAN. So here in this one, outer shell electrons are total 7 electrons for each metal, and 4 ligands are present to each metal. So 4 into 2, 8 electrons. So from this bond which was shared by 1 electron, so that is 1. Here which this metal got 2 electrons from this ligand, hence it is a 2 electrons total, which is got 18 electrons, which is also equal to the atomic inert gas atomic number. Hence this complex also stable. Like this, Sidjwick was explained the coordination bond is formed between metal and ligand. All the ligands donates the electrons to the metal and forms the coordinate covalent bond. He also explained the EAN. EAN is nothing but effective atomic number. Based on the effective atomic number, he was explained whether that complex is stable or not, whether that complex is diamagnetic or paramagnetic. If EAN value of any central metal atom is equals to inert gas atomic number, then those are stable and also diamagnetic. If EAN of the central metal atom is not equals to the inert gas atomic number, then those are unstable and also paramagnetic. Like this, Sidjwick was explained the stability of the complexes and also explains the structure of the complexes. Then after explaining the complex formation, also there is some limitations of this Sidjwick theory. Then first limitation, while formation of the complex, ligands are donating electrons to the central metal atom. So whenever all the ligands are donating the electron space to the central metal atom, then there may be possible to create negative charge on the metal. So which is leads to the instability of the complex. So this one is not explained by the Sidjwick. This drawback is not explained by the, so that complex instability was not, which is not explained by the Sidjwick. So which is one of the drawback of the Sidjwick. And another drawback of this theory, he was explained only the metal complexes which are formed due to only coordinate covalent bonds only. But many of the complexes are formed by covalent bond and also formed by the ionic bond, and also many of the complexes are formed with the intermediate nature of the linkages. But such type of the complexes are not explained by the Sidjwick. For example, if you see in this complex, like there is a bond between ligands and metal, those are ionic bonds. And in this complex, bonds are covalent bonds. And in this complex, the bonds are having intermediate nature, that is possessing ionic dipole attractions. So such type of the complexes are not explained by the Sidjwick. Sidjwick was explained only the complexes which are formed due to only coordinate covalent bond, not explained with the complexes which are formed with the ionic, covalent as well as dual nature of the complexes. And another drawback of this theory, many of the complexes which of the complexes compounds of the EAN value is not equal to the atomic number of the inert gas element, even though they are showing the highly stability, even though they are not showing the, many of the complexes are not showing the EAN value of the inert gas atomic number, but he couldn't explain the what such type of the complexes. Here if you see here, hexacyanoiron, in this complex iron atomic number is 26, whereas and oxidation number here total -6 ligands are present. On the sphere it is -3, so x minus 6 is equals to -3. Therefore this oxidation number is +3, so 26 minus 3 into 6 into 2, so total we will get 35. If you see like this in these complexes, which is no complex is EAN value is not equals to the inert gas atomic number, but he couldn't explain the such type of the complexes stability and also structure. Mainly it could not explain the stability of these complexes. And some of the complexes, even though this even atomic number is equals to the inert gas atomic number, but those complexes are not stable as expected. For example, if you see in this complex here, this complex atomic EAN number of the central metal atom is 36. So according to Sidjwick theory, if any metal central metal atom EAN value is equals to the inert gas atomic number, then it should be highly stable, it should be stable. But this complex EAN value is 36, even though it is not showing the more stability. So similarly in this complex also, it is 35, but even though it is showing the, it is not equals to the EAN of the inert gas element, but it is showing the stability. But he couldn't, Sidjwick theory couldn't explain the why such differences are present, what is the reason to get the stability. This theory was not explained. So these are the few drawbacks of the Sidgwick theory. So coming to the summary of this topic, today we have learned what are the postulates of the Sidgwick theory. Sidgwick theory mainly explains the bond is present between metal and ligand is coordinate covalent bond, and also explains the EAN. EAN is nothing but central metal atom electrons, total electrons of the central metal atoms, and also the metal which is gained electrons from the ligands are called it as a effective atomic number. The formula for the effective atomic number is central metal atom atomic number minus oxidation number plus n into coordination number. With this formula, with this EAN formula, we can say whether that complexes are stable, unstable, diamagnetic, paramagnetic. And coming to the drawbacks of theory, whenever ligands are donating electrons to the metal should get minimum partial negative charge, then it leads to the instability. It couldn't explain. And also, whenever EN value of some complexes are showing same inert gas value, atomic number, some complexes are not showing, not equal to the inert gas atomic number, but they are showing not results not properly. But these are the some drawbacks of the Sidgwick theory. This couldn't explain by the Sidgwick. To overcome all these drawbacks of the Sidgwick theory, next theory came out that the theory is called it as a valence bond theory. So next class we will discuss about the valence bond theory. Thank you for your patience listening.